In organic chemistry, when a chemist would like to synthesize or create a molecule in the lab, they're going to use a series of organic reactions. Oftentimes, there are things that occur naturally, and we are able to synthesize them or reproduce their formation in the lab by understanding their structure and by taking smaller molecules and reacting them with one another in order to create or produce larger molecules. A lot of products in your everyday life have been created by organic synthetic chemists who are applying the principles of organic reactions in order to do that. Now, there are hundreds of organic reactions that, if you study chemistry in university, you go over lots and lots of them. We're going to focus on a small number of organic reactions, and our focus is going to be on recognizing what type of reaction is going to occur and what the products will be. This approach is sometimes a bit more challenging because when you do study organic chemistry in university, you delve deeper into the structures and into the mechanisms or the processes that occur to allow these reactions to happen. I will, as I go through each of the reactions, I'll discuss the mechanisms a little bit if I think that it's appropriate and it might be helpful for you to understand what's happening and help to reduce the amount of memory work that you actually do need to do. We're going to focus on 6 reaction types, and they can be grouped. So as I'm going through each of them, I will group them for you and help you to recognize which ones can be paired together or viewed as opposites to one another. The first set of reactions that we look at are the addition, substitution, and elimination reactions. These ones involve, either as reactants or products, the hydrocarbons. So we're looking at alkenes, alkynes, alkanes, and aromatic hydrocarbons. For addition reactions, these are applicable to substances that involve a multiple bond. So we've got either a double or a triple bond. And what we're going to be doing is adding something across the double bond or the triple bond. The different substances that can be added are hydrogen, halogens such as X2, so in this case the X is the general formula, but we're talking about chlorine or fluorine or bromine or iodine, which are all diatomic. Water can be added, and hydrogen halides, or also referred to as HX, can be added across these double bonds or triple bonds. We're going to start with 2 reactants. We're going to have 1 product, and we're going to need to apply this rule called Markovnikov's rule, and I will talk about it when it's appropriate. So with these examples, we've got, in the first one, we've got an alkene, and we're adding bromine to this alkene. So bromine is Br, Br. So when you think about an addition reaction, you want to think about this molecule approaching the double bond. Okay, the double bond is a highly reactive center. Okay, there's electrons in a pi orbital, okay, above the molecule, so they're very welcoming and reactive to a bromine molecule. What happens here is the electrons from the double bond form a bond with the bromine. The electrons from here form a bond between this bromine and carbon atom. Okay, so essentially what we have, the bonds that are being broken, this double bond is being broken, this single bond is being broken, and we're forming 2 carbon-bromine bonds to each of the carbons. So although we've lost the double bond, okay, the carbons are still fully satisfied with 4 bonds. Another thing that we can add across the double bond is HBr. So this is referring to as HX. So we could have HF, HI, HCl. In this case, we're not adding the same atom. So here we had 2 bromine atoms that were added across. So it didn't matter which way we viewed the bromine molecule. With this one, because it's HBr, we've got a choice. We could add with the bromine going on to carbon 2, or we could add the other direction with the bromine going on to carbon 1. In order to make a decision about which product is going to be what is called our major product, okay, because essentially we are going to get a mixture of both. The major product is the one where the bromine, okay, so basically the one that's not the hydrogen, so this could be chlorine or fluorine or iodine. The bromine is added to the more substituted carbon of the two that are available. So in this case, this carbon here is more substituted. When we're talking about substitution in organic chemistry for a particular atom, we're looking at how many other carbon atoms are attached to it. So this one here is di-substituted because there are two other carbons attached to it. This carbon, on the other hand, is only mono-substituted. There's only one other carbon attached to it. So the major product comes from the bromine attaching here and the hydrogen attaching here. Okay, so we get 2-bromobutane in this case. Now the reason for this, the reason for Markovnikov's rule, is to do with the mechanism of the reaction and how it occurs. What happens in this reaction is in the first step of the process, the electrons from here form a bond to the hydrogen. And what that leaves is a carbon atom that is electron deficient. And so it essentially has a positive charge momentarily. And carbon does not want to have a charge at all. So this is a really unstable intermediate species. The intermediate species is most stable if the carbon that is positive is substituted. Okay? So although it's positive, there are electrons on either side of it, okay, and larger atoms on either side of it that are stabilizing it. Okay? So this is why the more common product, or the major product, has the bromine being attached to the more substituted carbon. In the case of adding water, it's the same scenario. When you add water across a double bond, you want to view the two pieces of water as hydrogen and OH. So you're adding H and OH. In this case, the hydroxyl group is going to be added to the more substituted carbon. So we're adding across this double bond. We've got the H and the OH. So if we do this reaction, we're actually producing an alcohol. Now in both of these examples, I've included the H atom just to help you to track the electrons, but in actual fact, if you drew the molecule and you didn't put the hydrogen atom there, that would be completely appropriate. In this last example, I've got an alkyne and I'm reacting it with iodine, so I'm adding iodine across this multiple bond. Now it's important to note that adding 1 mole of iodine would be different than a case where I added 2 moles of iodine. If I had 2 moles of iodine, this reaction would go further, okay, and we would actually produce tetraiodobutane, okay, because the first iodine molecule will add across to make the double bond, and then the second molecule could add across to make a single bond. The next type of reactions are substitution reactions. And these are connected to addition reactions by the way of the fact that they cover the other hydrocarbons that we've not yet discussed. So in addition reactions, those involve alkenes and alkynes. For substitution reactions, they involve alkanes and benzene or aromatic hydrocarbons. In these reactions, we're going to need a bit of help, okay, with UV light or a catalyst of FeBr3, okay, in order to allow the reaction to occur. These aren't going to be addition reactions, they're instead going to be a substitution reaction. So we'll look at how that occurs. So if you've got an alkane and you want to have a substitution reaction, what we're going to react it with is a halogen. Okay? And it needs to be not a hydrogen halide, but a pure halogen, so the diatomic molecule. And in this case, we're going to need some UV light. What's going to happen is one of the bromines in the Br2 is going to substitute with one of the hydrogens in the alkane. And this is going to occur in any of the hydrogens in the molecule. So in this case, you're going to get a real mixture of molecules, and that's something to consider when you're actually doing organic reactions, is that sometimes the reaction that you've selected is not ideal for making a pure product. This reaction can be useful in some cases though. Okay, so if we add bromine to this molecule, if we just leave it, it's not going to react at room temperature. We need some UV light in order to help the reaction to occur. And the reason that the UV light is needed is because an alkane on its own is not very reactive. So the carbon-hydrogen bonds are strong and will not easily be broken, okay, unless something really reactive comes along. So what the UV light does is it actually cleaves the bromine-bromine bond. When we have a cleaving bond, what's actually happening is one of the electrons from the bond is going to one atom and the other electron is going to the other atom. So what we end up with are radicals instead of ions. So we have these highly reactive species that have this one lone electron that really wants to react. So what occurs is we've got a hydrogen, okay, we've got a substitution. So one of the radical bromines will trade places with a hydrogen on the alkane molecule. So what we'll have is we'll have a bromine group on the alkane, and then the leftover bromine, okay, will form a bond with the hydrogen that's been removed from the alkane, and we're left with HBr. Okay. This will not subsequently react with the alkane. It's not reactive in the same way. Now, aromatic hydrocarbons will also undergo a substitution reaction. And that might seem unusual at first because it does have the double bond, so you might wonder, well, why doesn't an addition reaction occur? The reason an addition reaction doesn't occur is because of the unusual stability of this aromatic hydrocarbon. Okay, this alternating double, single bond system is very, very strong and it cannot be broken, okay, if at all possible. So rather than having an addition reaction where we lose the aromaticity or the alternating double, single bond system, we will have a substitution reaction. Okay, so there are hydrogens, okay, on each of the 6 carbons. So a bromine molecule, okay, can come in and we can have a substitution with the hydrogen. Okay, so same thing, okay, the bromine and the hydrogen atom essentially trade places, and so the benzene becomes substituted with bromine. The FeBr3 in this case is a catalyst. We don't need to know the details of it, but it does help to weaken the bonds in bromine. Okay. This substitution is not one that we're going to worry about, so you can cross that one off. Okay, it's just substituting one functional group for another. Now, elimination reactions are still groups, so these first 3 we're kind of putting together. Elimination reactions are actually the opposite of addition reactions. We're only going to focus on one elimination reaction, even though there are many. We're going to look at the elimination of water. Okay, so if we've got an alcohol and we remove water, we're going to be performing a dehydration reaction. Okay, so the dehydration of alcohol, we need a catalyst of sulfuric acid and we need heat in order to do this. So if I've got an alcohol and I heat it up in the presence of sulfuric acid, I'm going to eliminate water. So what happens is the hydroxyl on one of the carbons and a hydrogen on a neighboring carbon will be eliminated or removed as water. And as they're removed, okay, a double bond is formed. Okay, so it's exactly the opposite of addition reaction. In the addition reaction, we had a double bond and we added water across that double bond as H and OH. And this time we're eliminating those two H and OH as water. The next pair of reactions, oxidation reactions and reduction reactions, are opposites of one another. Before we discuss the actual reactions, we just need to have a quick discussion about what oxidation is. And for those of you in biology, you know that oxidation represents a loss of electrons. In organic molecules, when we go through reactions, it's not like an ionic bond, so we're not formally losing electrons, but essentially what's going to be happening is the carbon atom is going to be losing electron density. And when we study oxidation reduction reactions more formally later in the year, okay, you'll see that when we do track electrons using what's called oxidation numbers, you'll actually be able to see how come we view this as a loss of electrons. In terms of organic molecules, we need to look at the functional groups and compare their level of oxidation. If I have something like methane, there's no hydrogen on it. But if I go and look at another molecule, if I look at something that has a functional group of OH, or it's an alcohol, what's happened going from an alkane to an alcohol is that this carbon has become oxidized. So oxidation is viewed as the addition of oxygen or the loss of electrons. The reason this carbon is losing electrons is because of the electronegativity of oxygen. It's more electronegative, so it's pulling electron density away from the carbon atom. And that's why it's viewed as oxidation. Okay, thinking of our functional groups, the next functional group that will provide an even greater loss of electron density to the carbon would be our carbonyl. So alcohol to an aldehyde or ketone is further oxidized. And further to that is a carboxylic acid. So the more oxygens there are around a carbon atom, the more it's been oxidized, or the more there's been a loss of electrons. So when we look at this chain, if we're going this direction, okay, we're looking at oxidation. And if we're going the other direction, we're looking at reduction. In order to oxidize something, we need something called an oxidizing agent. And potassium permanganate is a common oxidizing agent, and there are other acids like HClO4 or HClO3. Anything that has a high amount of oxygen will often be a good oxidizing agent, or something that can be used to oxidize. Rather than worrying about particular oxidizing agents at this time, we're going to use a square brackets with an O, and that's a general way to show that we've added an oxidizing agent. What you're going to notice in these reactions is that we're not too worried about balancing the equations, and this is the case in a lot of organic reactions. Oftentimes in organic chemistry, we're focused on the product that we want, and we're not too worried about the other atoms that might be involved in side reactions or might be waste in the end. And this is an example of that scenario. So that's why we can just use a general square bracket with an O. So alcohols can be oxidized. And what we need to discuss is the difference between primary, secondary, and tertiary alcohols. When we talk about these differences, it's related to the number of carbons attached, okay, to the carbon holding the hydroxyl. So really the substitution of the carbon bearing the hydroxyl. So this one is monosubstituted, so this is a primary alcohol. This alcohol is disubstituted, so it's a secondary alcohol, and this alcohol is tertiary substituted. There are 3 other carbons attached to this particular carbon, so we say that it's tertiary. The reason it's important to distinguish between these types of alcohols is because they react differently and form different molecules. So when you see an alcohol and you see the square bracket with O, that means that the alcohol has been oxidized. And what you're going to do is simply change the functional group. So this OH simply becomes a carbonyl. Now, because this carbonyl is at the end of the chain, what we've produced in this case is an aldehyde. Okay, so primary alcohols are oxidized to aldehydes. Secondary alcohols, the OH again converts to a carbonyl. In this case, because in a secondary alcohol, the OH is somewhere in the middle of the chain, we've now produced a ketone. Tertiary alcohols cannot be oxidized. There's no space. I can't substitute this for a double bonded O, okay, because otherwise that would create 5 bonds on the carbon. So a tertiary alcohol is not going to be able to be oxidized. Now with aldehydes and ketones, when we look at further oxidation, we're looking at converting our carbonyl to a carboxylic acid. An aldehyde can undergo this oxidation. A ketone cannot. Okay? There's no space for me to add an OH. I can't replace an H with an OH here. Okay? I can't break the chain in order to have oxidation occur. I can only really replace a hydrogen. So it's not possible for a ketone to be oxidized. When we originally discussed aldehydes and ketones, we talked about the fact that they belong in different families because of their reactivity. And this is what I was referring to. Although they have the same functional group at first glance, their reactivity is different, and it's their reactivity and properties that really define whether they belong in the same family. And because there's something pretty majorly different about how they react, they're treated as 2 separate families. Okay. Now there's one really slight typo here, and we need to take that away. There should only be 4 carbons. Okay, so we started with butanol, we made butanal, and now we have butanoic acid. Reduction reactions are the opposite. We're going to focus on the reduction of a carbonyl carbon, so a C double bonded to O, being reduced to an alcohol. So we're going back up that chain that we had created a couple of slides ago. Reducing agents, common ones are a lithium aluminum hydride or hydrogen with a metal catalyst. Okay, this metal catalyst helps to weaken the bonds between the hydrogen atoms to add it to reduce the carbonyl. Just like we had the square bracket with the O, we'll use a square bracket with an H to represent a reducing agent. You can think of reduction reactions as an addition of hydrogen across the double bond. So when you've got an aldehyde, okay, I like to think about it as an addition across the double bond. So I'm losing the double bond, I'm bonding OH and then the CH, so I'm left with an alcohol of the same length. In this case, my ketone, I'm adding across the double bond, so one of the H's is added here, the other H is added to the oxygen, producing the alcohol. So if you've got an aldehyde, it reduces to a primary alcohol. If you've got a ketone, it reduces to a secondary alcohol. The last 2 types of reactions that we will look at are opposites of one another. We've got condensation reactions and hydrolysis reactions. These are both words that involve water, as you might have suspected. Condensation reactions in biology, they're often referred to, similar reactions to these are referred to as dehydration synthesis. What we're doing is taking smaller molecules and combining them to make a larger molecule. And in the process, we are losing water in the reaction. So hence the term condensation, or in biology, you discussed dehydration synthesis. Okay? Synthesis meaning you're making something, and then dehydration meaning you're losing water. The one example of a condensation reaction that we're going to look at is esterification. So we're going to be making esters. And esters are prepared by reacting a carboxylic acid with an alcohol in the presence of sulfuric acid and heat. In order to draw the products of these reactions, or to view the ester that's formed in these reactions, I find it easiest to point the functional groups at one another. So point, when you draw it, point the carboxylic acid group at the alcohol group. This way you'll be able to see the ester most easily. In these reactions, water is one of the products, and it comes from the hydrogen and the OH, okay, from the neighboring carboxylic acid and alcohol. So what we're doing here is losing water, and then you can think of this group as moving over and attaching at the oxygen. Okay, and you can see that this is the ester that's produced. So I've moved this ethyl group and I've attached it to the oxygen, and then what's in the blue box has left as water. And this program that I use to draw the molecules doesn't let me write it as H2O, so that's why you see it as OH2. We're going to do an experiment with these, and we're actually going to produce a few different esters. I think we produce 5. Okay, and this is one of the reactions that you'll get to see. So we've got, this is called benzoic acid. It's a bit of a common name. This is our carboxylic acid, okay, and this is our alcohol. So if you redraw the alcohol, it's a bit easier to see how the product is formed. So this makes the H2O, and this moves over and attaches to the O. And then you get the water. Esters tend to be aromatic. They have different scents, so fruit smells and mint smells and citronelle smells are all examples of esters. The opposite of these condensation reactions is a hydrolysis reaction. So by adding water, we're actually splitting a molecule into 2. So the only example of hydrolysis that we're going to look at is the opposite of our esterification. We're taking an ester this time, and we're reacting it with water in the presence of sulfuric acid and heat. And what it'll actually do is split the ester at the it'll split the ester here to produce the alcohol and the carboxylic acid. Okay, so in this case, we've got this ester, so I'm going to split it there, okay, and I make the carboxylic acid and the alcohol. So that concludes the lesson in organic reactions. On the handout that you have one series of practice reactions to work with. Okay, the key with these is to simply practice. You can just start by writing out the reactants, identifying which of the reactions will occur, and write the products. It's important to practice identifying what type of reaction. So is it addition, is it hydrolysis, is it substitution? Because those are the questions that you'll be doing in the assignment or the test. And this concludes our unit of organic chemistry. The focus is simply on the organic reactions.